Mhm. Good afternoon to everyone on Zoom. Can you hear me well? Let's test this. Test, test, test. Okay. For the ones that are attending on Zoom, can you make sure you guys give me a thumbs up that you can hear me well? Okay. Thank you, Rachel. And thank you guys. Okay, so we're at the 4:30 mark. We can go ahead and begin. It's recording, right? Yep. Okay, so a few things that I want to speak about before we continue where we left off last time is the midterms. I think the grades have been all released for all students, so you guys got yours back. Okay, that's good. Um, yeah, so we make sure that the TAs are met the deadline for that so that the grades are out by a certain time. And if you need to debrief any of your grades or you have any concerns, you can communicate with me or with them directly, whoever left off the comment regarding your deductions. Okay. The second thing I wanted to speak about is just to touch up on this webinar that's happening tomorrow. Um, it might be something that is too big for you to decide now at this stage of your academic life, but I figured I'd share it with you. So the department is having a webinar tomorrow, and I think it starts at 9:30. So if you're on campus and want to come out, it's going to be an HOA 101. Or if you want to attend on Teams, you can also do that. And basically, it's going to be regarding the master's program and the PhD program. So if you're interested in doing graduate school, nowadays with this, where are we at in this world? I mean, a master degree or a PhD degree will open many doors for you. So it's worth checking out. You can speak to other professors there, other lecturers maybe that are there that have done a PhD and or they have done a thesis with their masters. Because with the masters, you can do a thesis option or you can do a non-thesis option. So that is really open to you. So yeah, basically that's going to be it. So if you would like to register, you just click on the link. And I think this link was made by Dr. Yes, there's also going to be lunch provided there, so pizza, and there's going to be starts at 9:30 and ends around 3:45. I'm actually going to be part of the 2:45 session, so like the student alumni panel. So if you guys want to come out and ask any questions, I will be there as well. And yeah, that just tells the location. So to sign up, you just click here to register. So that is up to you, but I just figured I share it with you in case that it's interesting for you to if you wanted to come out. Okay, so that is that. Um, Also for the homework two is out. It was out today and it's gonna be due actually on, I believe, the 9th. Yeah, if we have some time today after the lecture, we can speak about it. But it's gonna be kind of similar to the other homeworks, but it's just we're gonna be regarding um what we speak about today and majorly the last lectures that we covered about the network layer. So that is that. That I just wanted to let you know that it's out. And that's it. We can go to our modules and where we are now. So we're still going to be in currently in week 11, homework two has been out. Last lecture, we're still in the network layer. So I just want to cover briefly what we talked about last lecture, a very quick a rundown of it, and then we can move on to today's lecture. So here's our general roadmap. I think last week we covered the network layer. We gave an overview. We talked about the data plane and control plane. Last lecture was mostly dedicated for what's inside a router. We talked about input ports, output ports, and the switching fabric and the architecture of the switching fabrics, how it was developed from old routers, and then how it transformed to what today modern routers have. We talked about buffer management. We know that the router has buffers and it will store incoming data and even data that is leaving. And we know that with the buffer management, there's some sort of schedule to release the packets, whether it's a first come, first serve. We have the round robin, we have the weighted way, and we also have priority way, where we prioritize specific traffic of packets over the others. Yeah, so that talks about the switching fabrics. We discussed those. We also talked about how much buffer is needed in the router. This is just talking about the scheduling policies. This is priority, round robin, weighted fair queuing. We talked about neutrality of how ISPs should share its resources and all that other stuff. Yeah, and this, I will repeat this. I will repeat this in this lecture today. I will talk about subnetting again, a little bit more in detail, and then we will continue with what we have. So we can start in the next lecture, which is this one. Okay, that is sharing, and sure that is sharing for Zoom. Okay, so as usual, the lecture is recorded and you can access it on the Zoom section. And some of the slides are borrowed from the book, so you can check those out on your own time. So where are we currently in the roadmap? We know that we discussed what's inside a router, and we discussed the data plane and the control plane. And we are studying the IP, the Internet Protocol. We discussed the datagram format, the very last lecture. We talked about addressing as well. This lecture, we're going to finish the IP, all of it. So we're going to talk about NATs, network address translation, and we're going to talk about IP version 6 as well. How we transform from IP version 4 to 6 and what's the reasons. We're actually going to talk a little bit about IP version 5 as well, and then we should wrap up. So I think next lecture will be, we'll talk about generalized forwarding and software-defined networking. So that is going to be for the next lecture. Okay, so this is the general format that we know when it comes to the network layer, and we're talking about layer 3. We know that it's between layer 2 and 3, obviously layer 2 and 4. So the network layer falls as a layer 3, and it falls just below the transport layer with TCP and UDP on top. And then we have the link layer and the physical layer that is there. We know that what comes inside the network layer is the selection of the algorithm that forwards the packets, because we know that when we're dealing with layer 3, we're dealing with external traffic, not only internal. So that we need to find the best algorithm for us to route the traffic. And then we have a forwarding table. We said that with the prefix, and we talked about the longest prefix match. And this is actually a question in your homework. That is how we can make sure that the data that is coming in is forwarded to the actual user. So based on the IP address, right? We also have the IP protocol. This is going to be defining the rules for the packets that are getting sent. So the datagram format, addressing, and how packets are handled as they move through routers. And then we also have the ICMP protocol that talks about error handling and signaling between routers. So this is what allows you, this is the feedback that comes back to you as an output when you do ping or trace route to trace route or ping a specific domain. So these are the messages that are coming in, like the number of hops, the maximum hops that you have, the time, the average time, how many packets were sent, lost, etc. So all the other stuff that we have. So this is a general overview of the format that we have. So we have a lot of things, and we covered it in the last lecture. We covered it again as well. So we know that we have the version. So this is related to the IP version protocol that we have. Could be IP version 4 or 6, depending on which one is being used. And we know that the different of bits are included. We have the header length. This talks about how long the header is. So in 32 bits or 128, depending on how it is. Type of the length, and we know that the total length is the entire datagram with the payload, including the header and including the data. So this is the overview summed length of the whole packet that we have. We also have the type of service. This is going to be related to for packets priority. So we know that it includes it's kind of like classified into this. This specific packet belongs to voice over IP. This belongs to HTTP. It belongs to video. So that is how we know, and we can prioritize specific data over another. We have time to live, and obviously this is going to be the time to live at each hop or each router that stops. So this prevents the packet from moving forever. And we know that time to live is an important factor when we talk about TCP. And we talked about congestion control, flow control, packet loss, packet drop, packet reordering. It's a really important factor such that we know when this time to live is out of this specific range of time, then we know how to retransmit the packets. This is the upper layer. So this is TCP or UDP, depending on which data protocol, data transmission that we use. Here the identification flags or the fragment offsets. This is used for fragmentation and reassembly when a packet is too large for the link. IP version 6 is gonna, when we talk about it today, is very simple and it reduces a lot of these actual kind of headers inside the datagram. And then we have the header checksum. This is to verify the data that it came in. It should belong to the actual user. We have the IP address 32 for sender and receiver because we're using IP version 4. And this is anytime, any optional stuff. It's really not used, but it's used kind of for testing security or for kind of records. And then we have our payload. And we said our payload is going to be about 40 bytes. So 20 bytes for TCP, 20 bytes for IP, plus the application layer data that we have. When we talked about subnetting in the last lecture, we talked about CIDR, and this is kind of classless interdomain routing. It really has nothing to do with subnetting, like the details of subnetting is just a cool way for us to know how much we actually subnet, how much of a partition of bits we have used for the network, and how many bits we have used for the host. So this is here we have 32-bit address. This is going to be 4 bytes or 4 octets, and each octet is going to have 8 bits. So if you count the number of bits and binaries that we're using the first 2 octets and 7 out of the first 3 out of the third octet. So that is 23 bits we are using. So we just put /23 after the address so that we know as a visual reader or a visual way for us to know how much we partitioned for the subnet. We always know as well that the ones and the binaries for the address, the ones always are for the network, and the zeros are for the host. So that's how we can identify what portion is being used by what. For the segmentation of the network, we know there's several ways to segment, and it's really going to be based on the admin of the network. Every admin can partition the network and have many subnets based on their motive. But some common ways are by geographical location, by departmental boundaries, or device types. Here we have a scenario that we have a specific business that is very local, small, and it's using only 20 to 30 computers. So there's only one broadcast address, there's only one LAN, there's only one router for this specific local area of network, and this specific router is acting the default gateway for everyone, every host that is included in that local Wi-Fi. So as the network grows, obviously traffic is going to increase because we have more hosts that are adding on, and it becomes harder to manage. So the solution for us to do is to segment the network so that it is still one local network, but we partition it in a way that within this local network, it is partitioned by or segmented by a motive that we have. So whether we want to segment based on the departments that we have in the business, like sales, finance, all that stuff. So it really depends. And subnetting is that each group of devices belong to a separate subnets. So, and also the clients must be configured on the specific subnet, so they belong to this actual subnet. And the IP address pool is divided into smaller groups. And this is the process that is called subnetting. So here's a current setup before the business has upgraded. They have one router, obviously, and all the floors that are there are using the actual router. We're using switches. And here, you're under the assumption of these switches are a layer 2 switch that only forwards the data between the floors and forwards the data also to the router. So devices can communicate directly, but this can cause high traffic due to too many broadcast messages. Maybe floor 1 does not really need to communicate at all with floor 2 or 1. So we don't need to really bother them with the broadcast messages with the incoming traffic. Also reduced performance as the network grows. If we cannot partition the network, the performance can decrease. We can have a bottleneck. And it's also difficult to troubleshoot as network admins want to have a deep dive into what the issue is. They can go to a specific subnet such that they know where it's coming from. So that is one way. So after we do the subnetting, the addresses are just going to be divided into smaller separate subnets, so one per floor. So we have a subnet per floor, and the devices remain the same. It's just that we have, for each subnet, we have a router that is connected to the main router, and that serves as a central connection to the internet. So the benefits of subnetting: reduced broadcast traffic. So each specific subnet has its own local traffic, better performance, easier troubleshooting, and improved security and control. So when we talk about IP address version 4, we know that the network, we have a network host, we have a network ID, and we have the host ID. So the network ID identifies the network. This is the number of subnets that we will have. And the host ID identifies a specific device on the network. When we talk generally about the idea of subnetting, we are only borrowing bits from the host. And we said the more bits that we borrow from the host, we have more subnets as part of the network, but there's a limitation of how many hosts we can assign per subnet. And we said the ones and zeros are the identifiers for us. So when we look at the binary, we know that the ones are the network bits and the zeros are going to be the host bits. So we have this specific address, which is 192.168.123.132. The network ID part is going to be the first 3 octets, and the host portion is going to be the last octet. So we are using a CIDR/24, meaning that we are using 24 bits for the network, and the last remainder 8 bits are for the host. And with the partitioning or the subnetting, when a computer sends data, it will check the destination to see if it's on the same network ID. Then if it's part of that subnet, then it will send it directly. If not, then it will send it to the default gateway router to reach another network. That means it's not part of that subnet. So here we have some examples. To speak really about the table first, these are classes that were already standardized. So those are really not subnetted. So we have class A that uses 8 bits for the network. We have class B that uses 16 or slash C that uses 24. So you can see the subnetting happening on these generalized classes. We can use class A, B, or C. But if we want to subnet, we borrow from the last 8 bits, that is the remainder for the host. So /24 is generally just class C we are partitioning. So when we take 24 bits for the network, that leaves us with 8 bits that are remainder for the host. And generally, to find out how many hosts we can allocate for is just 2 to the power of that number. So 2 to the power of 8 is going to be 256, but we always minus 2 that is used for network and broadcast messages. And then you kind of see the idea here that it's replicated when we borrow more bits. That leaves us with less bits for the host, and that leaves us with less number of hosts that we can allocate. So when we do /30, we're borrowing 30 bits for the network. 2 hosts are being used, which gives us a total of 2 hosts for each subnet. Here, just a general table for class B. We know class B uses only 16 bits. And here's just trying to show you that when we borrow more bits, what is going to be the result that we have. So we can directly see this table, and if you're looking at it from kind of like a network admin or a business owner, you can know that with your specific company, you have about 30 employees. So you really don't need to have all those bits for the host. What we can do is we can go directly into /27. That gives us a number of 30 hosts. So we can just be more efficient and we can leave the remainder for the network. And the general idea is that when we borrow more bits for the network, it leaves us with less number of hosts and increased number of subnets. So you can see the pattern here. When we do /17, we have the two of subnets for the network and 32,766 for the number of hosts. And it kind of keeps going down, and similarly to what we have in the last slides. This is just class C. We know class C is just 24. So anything above 24 is going to be the subnetting that we are doing. So the same idea here. We borrow more bits, we have more subnets, less hosts. And here is a general idea that we have of a network being split into 6 subnets. And we are using /27. So we know that we have 6 different subnets here. And we have a mainline default router. And there's devices within that router that are using devices that are using IPs that is available to them between a specific number of bits, obviously. So you can see that the first circle or the first subnet is using any addresses from 89.0 to 0.32. So the addresses have to be in between for the first subnet. And then it makes its way up until we get to obviously 255 or 254, depending on the addresses that are used for broadcasting and for the network. So that just makes it more local, more neat for us to have something like this where it's partitioned by device types or by departments or by location. And then it reduces also the traffic and improves clarity. So for us, so is subnetting clear for everyone? Okay, that's good. So we continue on how does the computers get actual IPs? So we want to get an IP address. We have actually 2 ways to do it. So we have 2 questions, and the questions that we ask ourselves is, how does a host get an IP address within its network host part of the address? And how does a network get IP address for itself? So the network part of the address itself. So for question 1, if you have a phone or you have a laptop, you go to a specific network and you're joining the network, you are getting an IP address, obviously from the network. And then from a network perspective, like UCF or your home Wi-Fi, how does it get its own range of IPs so that it can assign for users? So we also need to understand that. So we actually have 2 ways. First way is kind of manual. It can be hard-coded manually by a system or admin in the configuration. So if you, for example, you can on Unix, you can go out and modify the IP addresses within the given range that you have, and then you choose a manual IP address that is set by, if the IP address is already assigned to another host, and that specific license for the host still remains active, then you cannot actually have the IP address. And then the more modern way or dynamic way is using the DHCP server, which is a dynamic host configuration protocol that assigns IP addresses automatically. So when we say the DHCP is plug and play, meaning that when a device joins the network, the device will obviously send a probe request to the server, and the server is going to say, hey, you want an IP address, I'll assign you this. And it's just kind of like a 2-way communication agreed upon. So similar to like TCP acknowledge, sent and acknowledgement. So we'll see how that works also visually. So here we have, at the bottom of the image, we have subnet 1, and we have 2 devices here that are using, that are already part of the subnet, but we have a new client that comes in and wants an IP address. So they send a DHCP request. Obviously, they have a switch that would forward it. And we can have another switch that forwards it to the DHCP server. The server is going to just reply and assign an IP address within the given pool that is not already being used by another client. So this is generally how it works. So, and the idea is that every network infrastructure would have some sort of server that is like that is configured just to assign IP addresses. And we don't need to have many DHCP server. We can just have one per network infrastructure. So we don't have to have a DHCP server inside each subnet. We can just have one that is part of the network that can assign for other subnets as well. So that is generally how an IP, a new client gets an IP address kind of like more dynamically, okay? Okay, so the DHB Dynamic Host Configuration Protocol, we know gets its IP address. A host gets an IP address from there when it joins the network. And the host can also renew its IP lease while it's still connected. And this approach allows reusing IP addresses. So once a device connects, the address can be assigned to another. So when you're going and using a Wi-Fi and you're not planning to stay there for a long time, then what we can do is that we can have a lease for your IP address such that when you disconnect, it can be assigned to someone else. And it's very sufficient. This approach is very sufficient for 5G networks and mobile users who are just going to frequently join and leave. So the overview of DHCP again, the host first broadcasts a DHCP discover message to find any available servers. The server would reply with an offer containing a message saying, hey, we have this available IP for you. And then the host would send a message back to saying that I accept the offer. And then the server confirms by sending an acknowledgement and it officially assigns that IP address. So here I want to show you the setup of the DHCP where it would fall in a given network infrastructure that we have. So here we have a router, we have an access point, and an AP, and we have different hosts, we have different subnets that we know of. So usually the DHCP server is going to be here in red, and it's going to manage and distribute IP addresses across the whole network. We said we only need one specific server. We don't need multiple servers per subnet. So it's oftenly co-located with the router. So your home Wi-Fi's, when you have a specific router, the DHCP server, it's also configured within that router to assign IP addresses. So that's why you see in house Wi-Fi's, you're not using an actual server for that. But bigger infrastructures like colleges, hospitals have a specific server that is running to assign IP addresses. So this specific server provides services for all subnets and all newer devices that come on and trying to join. So when a client comes in and needs an IP address, we talked about how it would get an IP address by discovering the server, sending a request. The server sends a message back and say, hey, here's the IP address. And then they just confirm between each other and the IP address gets assigned to that specific client. So let us see how this works and a full demonstration. So this is going to be the DHCP process between a client and a server. So we have a client on the right-hand side, and we have a server that has an IP address, and we're going to see the exchange messages between them. So the first thing that the client will do, obviously, since they are in need of an IP address, they will send a discover message saying, is there any DHCP server out there? And here the message details is shown. So the source address is 0.0.0.0, meaning that the client does not have an IP address just yet. The destination address is going to be 255 for all the bytes or for all octets, meaning it's sending a broadcast to all devices on the local network because we are trying to probe for that server first. And the transaction ID is kind of like a match to helps match responses to requests. So it's just kind of like an identifier for this specific request. So next we jump onto the server. The server would say, hey, I have an offer for you, and there's an available IP that is available for use. And so the detailed message of that offer would be obviously the source would be the source of the server that is 223.1.25. And the destination that it's sending to is also going to be broadcasted the same way that it was broadcasted in the initial request. Here we have the offered IP, which is the YIADDR. This is the proposed IP address that is trying to give to the client. And the lifetime is the amount of time that this IP address is available for unless it needs to be released. So that is 1 hour. And here, just a specific note, when we talk about the RFCs, the standardized protocols or standardized information that is coming from the DHCP. If a client remembers a previously assigned IP, it can skip the discover and offer steps. So once you come to a specific Wi-Fi infrastructure and you've been assigned an IP before, you don't really need to send another request to find a newer IP. We'll try to assign you the same IP that you had previously, unless the IP is being used. So what would happen next is that the client would send a message saying, hey, okay, I would like to use this IP address, and here's the details of the message. The IP address is still 0 because there's no address that is accepted upon yet, or the destination is going to be also broadcasted like usual. The requested IP is going to be the one that it is actually was trying to be assigned by the server, and the lifetime is going to remain the same in the official offer. And then finally, the server would say, hey, I confirm the allocations that you wanted, and it tells the client you got the specific IP. So it confirms the setup, and the client now can communicate with its assigned IP. We no longer need to broadcast if we have newer messages, we no longer need to broadcast for the destination, because the destination is the address that is the YIADDR address that ends in 0.2.4. So the transaction ID, something to know here, the transaction ID changes per message. So you see there's an increment of 654, 654. So for each request and reply, it is 1 transaction ID. And so that is the same for the other requests that we have. So other requests and acknowledgement. Does that make sense how a laptop gets an IP? Okay. It also has another feature. So not only it provides IPs to clients, it also supplies other important configuration details for proper communication. So these details include like the default gateway, so the first hop router that connects the clients to other networks. Also DNS resolvers, so the DNS server name and IP address, so used to translate domain names into the IPs. And also the network mask, so which is the subnet mask that identifies the network and host portion of the address. So these extra parameters allows the client to automatically join and function correctly in the network without manual setup. So it kind of remembers those the initial time it connects. So this slide shows a simple DHCP example where the DHCP server is built exactly on the router, and we said that it can be configured on the router. And we have a laptop or a client here that is joining the network and preparing to send a request. So here we would have this specific client that is trying to send a request. And so the client starts the process of gaining an IP address. So the DHCP is actually a protocol, and it works on top of the UDP and IP, Ethernet, and the physical layers. So it would send a message, which is encapsulated with multiple layers. You can see we know that the DHCP is built on top of all these other layers that we see, like UDP and IP, Ethernet, and the physical aspect. So it is encapsulated with multiple layers. So the DHCP is messages is inside the UDP, and the UDP is inside the IP, and the IP is inside the Ethernet. So the Ethernet frame would carry the message to the broadcast message to the LAN destination. So it routes it to the DHCP server so that the client can gain an IP address. And the router receives that information and processes it. So it would use demultiplexing, which we know that it takes the message and demultiplexes it. So the Ethernet layer would demultiplex to the IP, and the IP demultiplexes to the UDP, and it goes on so forth till it gets to the DHCP application. And then the server would prepare a reply to that client. So that is the other way that we have. So we can have a specific server for the DHCP, and we've seen how that works. We can have it within the router, and this is how it actually works as well. So it's kind of like generally the same. It's whether it's configured on the router or we have a specific server that is set up for it. So obviously the server that is built into the router is gonna formulate an acknowledgement message. And basically the acknowledgement message is gonna say, here's your IP address, the IP address of the first hop router, the DNS resolver, which gives the IP address, and the DNS server that goes with it. And then it would send a reply back to the client, and which is also encapsulated. And then it makes its way up by using demultiplexing. So it goes through each layer. Obviously, it touches the Ethernet, IP, UDP, and it goes to the DHCP for the clients. So now the client knows its IP, and it knows its IP address, and it knows the name of the DNS server and the IP of its first hop router that we have. So earlier we discussed how the host gets an IP address using DHCP. Now we want to shift to the entire network. So we know that we are dealing with two ways. We are dealing with clients and we're dealing with the actual network. How does the network get its pool of addresses? Like the university or the company, how does it get its subnet part of the IP address? And actually it's gonna get it from the internet service provider. So you're gonna get your pool or range of addresses from the ISP, like Spectrum, Verizon, or whatever you have. And the ISPs owns a large address block that is shown here that we have. And that specific address. And the ISPs, they can subdivide and allocate partitions or portions of its addresses to block to multiple organizations. So in the example here, the ISPs divides its /20 into 8 smaller /23 subnets, so that each organization from 0 to organization 7 that we have here receives one of those subnets. And it's kind of related to the idea of subnetting that we have. The ISPs just get a pool range of addresses. They subnet depending on the organization size that we have. And this allows that each organization, maybe each house, has a range of addresses that goes from the allocated number of bits to how much it's allocated for, like we've seen in the last exam with the subnets, where we have one router and we have 6 other subnets that are part of that. So it is the same thing with generally how the network gets its pool of range of addresses. So basically from the ISPs, it's subnets. The ISPs would subnet it based on the organizations that we have. Here, this slide shows a hierarchical addressing. Um, and it just makes it more efficient. And it helps makes the internet routing more efficient, meaning that here we have various organizations, so 0 to 7. And we know that each organization has its own subnet. So it means that they have their own range or their pool of addresses. And all of these subnets that you can see here is fly by night by the ISPs. So meaning that these specific subnets were supplied by the ISPs. So instead of advertising every individual route, the ISPs can kind of combine them into a single summary route. So we have one summary route where the internet would, it's kind of like saying, hey, we have different subnets, but we want to use one public IP or one specific IP to communicate with these organizations. So the ISP would say, hey, I have a specific address that we see here, and it said, send me anything with the address beginning with this specific number. And the ISPs can communicate with the organization. So this is just a hierarchical way of communication with the internet and the other organizations that we have. And then larger ISPs, like we see at the bottom, now ISPSR/US, can also summarize their addresses ranges. So they take their ranges, and that is depending on the subnets that they have when it advertises to the global internet. So this is just a hierarchical structure that kind of keeps the routing table smaller and makes routing updates much faster and more scalable. And this kind of slide shows what's happening. So we know that organization 1 is going to be part of the fly-by-night ISPs. And we want to see if what happens once a specific organization moves out. So here we have organization 1. It would move out of the fly-by-night ISPs. So the organization keep its same address block that we have, where it was on the top, but it's now physically connected to a different ISP. So the ISP-RS becomes responsible for reaching out to the network and the advertising between that specific organization and the global ISP. So this is just saying that if you're a part of one specific ISP and you jump to another ISP, the other ISP will be responsible for you and it will communicate with the global internet. Right. So the general idea would be like we have two kind of categories, and each categories has subnets. And for each category, we have one address that would be communicating with the internet. So we have. So that makes sure that when we move an organization, it is current, it's efficiently being communicated, and it's still having its own address range, but it's still also connected to the global ISPs. And you see here in red, so it says send me anything with the address beginning in 199.31.0.6, which is the public IP by the ISPs or the /US, or we can use the organization IP that we have, which is came from the top genre or the top category to the bottom category. So it's kind of the same idea. So it can either be joined with the public IP that we have, or it can be communicated directly with its original IP address. And here the blue arrow would just communicate with either the specific category or communicate specifically with the organization. So that is the idea. So internet routers will prefer a more specific route over the broader range. So as a result, we have the packets to organization 1 reach the correct network through the new ISP that we have. So this could happen where you are moving from a different, maybe ISP from a different company to another company. So this is just trying to show you that we can have multiple ISPs and how they communicate with the internet. before we wrap up IPs, so just there's a last few things. The first thing that we have is that how does the ISPs get its block of IP addresses? And this is allocated by the ICANN, um, which stands for Internet Corporation for Assigned Names and Numbers. And this specific corporation distribute block of addresses to 5 regional locations or 5 local regional registries around the world that we have. And these specific regional registries can then allocate to local ISPs and organizations. So these are the registries, there are 5, they are around the world. And they are placed geographically, obviously, and those would communicate with the local ISPs, and they would give them their range of addresses. Also, if you don't remember, when we talked about the DNS resolvers, ICANN also manages the DNS root zone, so that controls the top level domains like .com, .edu, and .org. And then obviously we know the answer to this, and we say is that why we moved from IP version 4 to 6, because we know that the addresses within IP version 4, the 32 bits is really not enough. And actually the ICANN has allocated the last chunk of IP addresses in 2011. So the IP version 4 is actually exhausted. So that's why we are needing an IP version 6, which has been deployed. NAT's network address translation helped with IP version 4 a lot, and we're gonna see how it actually works. It kind of like extended the IP version 4 life by reusing private IPs inside public IPs, and we'll see how this works. But obviously the long-term resolution is IP version 6, which is 128 bits, and that is gonna be covering a huge number of hosts where we don't need to worry about this issue again. And this is just a quote, or Vince Cerf is reflecting on the decision why there's only 32 bits addresses in IP version 4, and no one actually knew how much addresses we actually needed. So it was kind of like deployed with that specific addresses, but over time, where technology has emerged, and actually the one factor of that emerges IoT devices is made us need an IP version, a newer IP version protocol. So IP version 6. So let's go back to our roadmap and see where we are. We already covered the network layer overview. We talked about what's inside a router. We talked about the IP, the internet protocol. We talked about addressing the datagram format. So next we have network address translation and IP version 6 that we will talk about. And this will be obviously for the next lecture. So the idea of NATs that we have, network address translation, is basically gonna, we have here in the specific figure, we have a local network, and within this local network, we have private IPs, like we see that ends with 0.1, 0.2, 0.3 for those devices. And we have a router that is installed that also has a private IP that communicates with the internal private IPs. The network address came and say, hey, you can have private IPs locally, but then what I can do is I can take those private IPs, and when you want to communicate externally, I can have one external general IP address. So let's see how this works exactly. So datagrams that are with the source and destination. This network have the address, which is /24 for source and destination as usual. And that is the typical range for this subnet. And then we have, once it reaches the external traffic, we have this specific IP address. So all datagrams that are leaving from the local network have the same IP address, which is 138.76.29.7, but different source port numbers. And the idea of source port numbers is to actually localize and know which specific private IP belongs to what. So that is the idea. So let's continue. And this is kind of like a mechanism that extended, as we said, the life of IP version 4. So basically, the NAT just came and said, hey, when packets move from the private side to the public side or to the outside world, all traffic would appear like it would came from a single host. So, and the NAT router would have kind of multiple IPs behind it, private ones, and then that are active. Okay, so let's see here. So all devices are using 32-bit addresses, so that we see in the last slide. And these are working internally inside the local network, and they are not routable to the internet. So the NAT router handles all communication between these private IPs and the outside world. And actually, the NAT offers several things. So only one public IP address is needed for all devices, and internal addresses can change without affecting the internet side. So their private IPs can communicate locally within themselves, but once they communicate externally, we're going to need a public IP for that. You can change the ISPs without reconfiguring local devices, so that is also one advantage. And it also adds security since internal hosts aren't directly visible from the outside. So, for example, if you're in an infrastructure and let's say you're a part of a specific department, let's say finance, and within finance, we have maybe like 10 employees and we have private IPs assigned for every employee. So when we reach external traffic or when we ping or we send data that is forwarded to externally, the other side, which is the destination, would only see a public IP. It cannot locate where the traffic came from. So that is kind of one way, kind of like similar to having a VPN for these devices. So that is an idea of some sort of security for these private IPs. So for outgoing datagrams, the router would replace the source IP address and port number with its own public IP address. We know that. So when a local user that has a private IP wants to communicate externally, they will reach to the NAT router, and the NAT router would receive information from the local IP that has a local IP address, private one, and also has a source port number that is assigned to it. So the remote servers then reply to this new public IP and port, so it does not reply to the original private addresses that we have. And the router actually itself, the NAT router that we have, that is that works in between the public and private IPs, kind of has like a table that remembers all the local private IPs and their port numbers, and such that when they are communicating with each other, it maps every source IP and every source port such that we can know what's inside the network. So it compare the replies, because when the reply comes back from the other side, it goes to the NAT router, and the NAT router has a table that knows to forward it to which private IP. And we'll see a demonstration of this soon. Yep, that is as known, that's when incoming packets. So this is kind of like a programmable way where you can do the configurations for your addresses, right? And here what we have is that we have the private connections, and the private connections can be an address like that we can see here on the top. Let me just where is this? Okay, so we have private connections as we seen in the last figure. These are the private ones. We have port numbers for these. And then once they reach the NAT router, the router would assign one public IP for those. So that is the same IP address, 29.27. And it also gives them an external port number. So 4001, 4002, and 4003. And the NAT router would remember this table. It has that mapping. So the private IPs with their private ports and the public IPs with their public ports. So what's changing only is that on the private side, obviously the IP is changing and the port is changing. The public port is the public IP is gonna remain the same for each device, and the public port is gonna change for each device. Does that make sense so far? Like what we have discussed. So we have local machines that are using private IPs and how they would transform when they reach external traffic. Okay. Okay, let's see how this works. So this is kind of like a demonstration of what we spoke about in the big overview. So we have a router obviously in place, and not a NAT router. And a NAT router is not really a specific router. It's just a router that has the NAT protocol configured on it. So we don't need another NAT router for the demonstration. So we have the local IPs, private ones, that have private IPs, obviously, as you see here on the right-hand side. And we have a public IP that we have on the left-hand side. And we have the translation table that kind of is kept by the router to remember where the packets are coming from, which private IP, and how it transfers it to the public IP. Okay, so the first host that we see that ends with the address ends with 0.01 would send a datagram to a specific address that we have, the destination. Let me use the laser for this. Okay. So we have this specific host that is trying to send a datagram to this specific address. And we know this is the port number is 80. That's usually an HTTP traffic, or no, actually that is not related to the port numbers, the actual port numbers for the protocols. So this is the internal port number. So the datagram leaves the local network, it heads to the router. The router would get the traffic from the local, and it would assign obviously a public IP, which is the same as this one, and it would assign it a public port, and the destination remains the same. And this is the same destination that the local private IP wanted to send to. So on the LAN side, and the LAN is usually the local traffic, we have the same, we have the IP with the specific port number. So this is the local traffic. On the WAN side, we have the replaced public IP and the replaced public port number that we have. Okay. So the NAT router would change that. Does that make sense for the initial step? Okay. Then we would have a reply from the web server to the destination. So when it replies to the same public IP and public port number that we have. That is just getting our typical reply back. And then the fourth step is lastly, the router would say, hey, I want to reverse the incoming packets to the actual private IP that we have. So it uses the source is obviously going to be the sender, and the destination is going to be the original IP address, the private one with its private port number that is being used in the initial step. So that makes sense, right? For each coming local device, how it connects to external traffic and how the NAT would transfer the local IP to a public IP. So NAT can be controversial, and because there are several reasons. And the first reason is that some argue that the router should only handle up to layer 3, but the NAT is actually operating beyond layer 3. It's using kind of the transport layer by using the port numbers with that. And others say, well, while this can be an issue, we'll have a shortage with IP version 4, so the NAT solves this issue. So it works around it. It can also violate end-to-end arguments, meaning that the NAT changes port numbers and interferes with direct communication between hosts, because we know that within a specific application, how hosts would communicate is by port numbers. And also NAT is going to be traversal, meaning that it becomes difficult for the client outside the network to reach the server behind the NAT. But despite all these controversial brought up ideas, it's actually here to stay. So it is being used by home Wi-Fi's, enterprise systems, even 4G and 5G cellular networks. So it remains essential for connecting millions of private IPs to public internet with limited IP addresses that we have. And lastly, what we have in the lecture is to talk about IP version 6. And then you might ask yourself, what happened to IP version 5? And IP version 5 was kind of like an experimental streaming protocol. Because when the time, I believe, uh, from what I know, is that the IP version 5 was deployed kind of at a time where the exhaustion of IP version 4 wasn't an issue. So it became a extreme experimenting streaming protocol, and I think it was called ST or ST2, and it used 32 bits. It did not do any expansion of the bits, so it remained 32. So it never became the standard that we that solves the exhaustion with IP version 4. That's why we moved on to IP version 6 that expanded the number of bits. So kind of IP version 5 kind of like did exist, but it kind of didn't make it big. So it's kind of like the beta version of Netflix that has like never launched. Okay, and then we move to IP version 6, which is actually a lot simpler than IP version 4. And we know the main motive for IP version 6 is that because IP version 4 was running out of addresses that is fully allocated, and it was designed to expand the address systematically and dramatically and improve um, the future proof of the internet. And beyond the addresses, it actually came with other motives. Actually, speed is one of it. Packet processing is another. And obviously, the byte header size has increased as well. And it came with other features like flow labeling that allows the routers to handle certain traffic flows, such as like streaming or real-time data that is different from the regular traffic. So this is just trying to show you the diagram format, and you can see how less it looks compared to IP version 4, where we had a lot of things. So here it's very simple. So first thing is that we are using 128 bits for the source and destination. Compared to IP version 4, we're using 32. So this IP version 6 with the 132 provides almost unlimited number of unique IPs. So it solves the exhaustion problem. The next thing that we have is the flow label that allows the packets that allows kind of an identification where the packets belong to the same flow. It's kind of like the checks that we have. The priority field exists still, and this is kind of like for sensitive datagrams or which packets should move on forward during congestion. It's kind of like the scheduling mechanisms that we talked about. What's missing with IP version 4? So there's no checksums. This kind of speeds processing at routers. There's no fragmentation or reassembly. That's handled actually by the source and destination hosts. And there's no option fields. So instead, the IP version 6 uses extension headers and additional features. And then obviously we also have the payload data that is typical that we would have in both versions. The transition from IP version 4 to 6 was not actually instant, and we still haven't fully transitioned if you're asking yourself that questions. So now all routers can be upgraded at a time. So here they're saying no flag days, meaning where everyone switches together. So the main challenge that we have is that how can the internet function with IP version 4 and IP version 6 still existing during the transition period? Because some laptops right now are using both, they're dual booted. And the key solution to this is actually going to be tunneling. where we tunnel the incoming packets that we have or the ongoing packets. So tunneling is the idea is that the IP version datagram is being going to be carried out inside the IP version 4 datagram. So it's called a packet within a packet. So it's kind of like encapsulated packets within packets. That allows the IP version 6 traffic to move across the IP version routers, IP version 4 routers that haven't been upgraded. And tunneling is actually not even just used in modern networks, it's also used by 4G and 5G, because that is actually two different systems that we have as well. So we will see how tunneling works as well. So in this example, we have an IP version 4 datagram, and basically we're just gonna take the IP version 6 datagram and just like kind of condense it with the IP version datagram. So IP version field still gonna remain the same, and the IP version payload is gonna be also the same. So that is how the idea of how we can solve this routers where they don't coexist with IP version 4 and 6. And with the encapsulated packet reaches IP version 6 or reaches the IP version 6 capable router, the IP header 4, version 4 is going to be removed. And then the IP version 6 datagram would just continue to its destination normally. So let us see how this works when we speak about routers. So we have here Ethernet connecting to IP version 6 routers. So we have 4 routers here, A, B, E, and F. And they're all using IP version 6. So we don't have an issue here that is going on. So communication can be exchanged normally, and we don't need to use tunneling at all. So the IP version 6 datagram here is going to be carried out inside the physical layer frame. This is just typical when we speak about the OSI model, and this represents direct IP version 6 communication. So there is no translation or tunneling is needed just yet. Now imagine the scenario changes for us where IP versions 4 and 6 kind of are kind of both included. And we need a way to separate the IP version 4 from the 6. So here we have 4 routers as well, although router B and E is using IP version 4. So we have to kind of like make it coexist. So when routers B and E need to communicate, they need to communicate only through the IP version 4. And then even though they are using IP version 4 and 6. Okay, so to make this possible, we're gonna use tunneling, essentially a virtual link that connects two IP version 6 routers across an IP version 4. So let's see how this works. So we have an IP version 6, and the datagram is going to be placed inside the IP version 4 packets, so it allows it to travel to the IP version 4 routers in a fashioned way. And this is the idea that is called tunneling. So that the entire IP version datagram is going to be inside the IP version 4 datagram. Once we reach the specific routers of the IP version 4, the IP version 6 datagram goes back to its normal way. So let's see the logical view and physical view of the tunneling. The logical view is that there's just going to be a communication. And the physical view is that we have address C and D is using IP version 4. So how do we work with this? So from A to B, this is considered as flow because we're using a flow with IP version 6. It is one of the known headers in the datagram. Obviously, the source is going to be A to F. So we're trying to get from router A all the way to router F. We have our data and the physical the first transition from A to B using IP version 6. There is no issue with A to B so far. When we go to B to E, we are using IP version 4. So the flow is the same. It's going to be from A to F. The flow identifier is also going to be X. The data is also the same. It's just that when we travel from B to C, we have IP6 inside IP version 4. Then we continue the same. The source and destination is going from B to E. So we the stalled IP version 6 is included inside the IP version 4. And here, this is the last hop, you would say, for IP version 4. So stall, the IP version 6 is inside the IP version 4. And then here it goes back to its regular way. Does everyone understand it? Is it clear? Okay. So note the source and destination remains the same, A and F, regardless of the tunneling. So if we're tunneling through IP version 4 routers or version 6, the source and destination is going to be remain the same because we can input a specific source. And this is the idea of dual booting. Some servers or some host when you're communicating or some the specific web pages there are or servers that are using IP version 6. And you might be using IP version 4. You can still communicate with each other. And this is kind of talking about a statistical view of IP version 6. And I actually have updated this with more recently. And if you want to mess with this website, it is by Google. You can access it. Basically, statistically speaking, that IP version 6 has grown, and it's currently reaching around 50% of Google Play users. So this just shows that IP version 6 is no longer experimental. It's actually becoming the new normal traffic or the normal internet traffic. And we can see that ISPs and mobile carriers have led the growth, especially in regions where like newer infrastructure supports IP version 6. And also the NIST, according to the NIST, and the US government is also pushing IP version 6 adoption. So almost half of federal domains now support IPv6 connectivity. So this is just trying to show you that IP version 6 is it's on its way to replace IP version 4 as the primary protocol of the internet communication. We know that even that IP version 6 is established and has a dramatic growth. If we speak about a timeline, IP version 6 was actually standardized in the 1990s, but here yet we are 25 years later, still transitioning. And you can think from 1990s to now, how much the internet has changed in time from static web pages to social networks, video streaming, and real-time communication. So while application level innovation has changed so fast, why did the infrastructure from IP version 4 to 6 has not changed the same? So it's actually very slow to think about it. So that leads us to a question saying why, what makes a protocol upgrade so difficult? Even though we have a need for it and it's actually obvious. So the why comes from various things. The first thing is that IP version 4 still works well and it's still being used. We know NATs are expanding the life of IP version 4 yet still. There's no immediate business incentive to switch. So businesses don't have an incentive of switching. Another issue could be compatible issues. So IP version 6 and 4 are not directly, cannot be maybe interable, like to interpret them. Also the cost and complexity of upgrading routers, upgrading switches, firewalls, and software that can be an expense. And gradual transition is that both protocols must coexist. So like dual stacking or tunneling for that to happen. So it's on its way with time. So we have finished everything so far. Next lecture, we will talk about generalized forwarding software. Okay, yeah. No, they're like, we mean like in terms of assignments?
Like, say you got a point over my house or something, and I'm like working on the device, and I want to get on. I'm still buying IPv4 for it, or only IPv6 router.
I'm not actually, I'm not sure when it comes to the business aspect of it, like, obviously you're contacting an ISP, and they just come, either you have your own router and they configure it for you, or they're giving you a router and it's already pre-configured by them. So I'm not sure if it's an IP version 4 or 6, but we know the exhaustion of IP version 4 addresses has been automatically done. So most likely is gonna be either dual booted or completely using IP version 6. And you can check maybe your own devices, maybe when you're at home. And if you do ifconfig, you can, if you have two different addresses, that mean you're dual booted to use both. So the idea still exists. Yeah, so that is that. We will touch up on this next week and we will finish the network layer. I hope that so far it's very clear and understandable. So to everyone on Zoom, I'll see you next Monday. And to everyone in class, I'll also see you next week and wish you have a good weekend.